Welcome on wireless mobile communication online course. It is the lecture number 8 and part 2. In previous lecture we have seen that the recap of the previous lectures, that is the free space propagation, and we have dealt the free space equation. During derivation we have seen that the free space equations is having only the valid in predictor. This is model only for shows only the direct line of path, direct line of side. So it is, this model is only a LOS signals. So they are the certain drawback in of free space equations. First is the free space model is a valid predictor, means d is not equal to 0. And second drawback is this model assumes only a line of sight signals. The question arises that where should we place the antenna, and in which electromagnetic lines of force. So this is a major problem in a mobile radio channel. A single direct path between the base station and the mobile is seldom the only the physical means for the propagation, where the free space model is given by the equation, that is the PLDB is equal to 10 log power to the received power, transmit power to the received power, minus 10 log G of T, G of R, that is the gain of antenna and gain of receiver, to pi r square and dr square. This is the freeze equation. In this equation is derived in the previous series modules. So the main answer is where we have put our antenna, at which place. So the answer is given by the fields of antenna. In fields of antenna we have shown that is our antenna, and this center of antenna, which is connected by a large physical dimension. This is nothing but it is the capital L, and there is a free open area. This is the free open area. This area is divided into the two parts, and we have having the center of this antenna. Again, from antenna and the division of the between this area is the near field of the antenna, and beyond this line and goes so far distance, that field is known as far field. This near field is again divided into two parts. One is the reactive and radiative part is the next field. It is also known as the Fresnel region, and this far field is also known as the Fraunhofer region. So the area which is from antenna and mid of this far field and near field, that is called the near field. Near field is divided again into two parts. One is reactive field region, and half of the portion from here and the started from this and this, between this two line, half of this region is called the reactive region, and after that from half of the rest of the region and part free space is known as far field. Our antenna, our receiver, which we have put in this region only in this region our antenna is working. So the near field is look like this. It is like this fashion I have shown there. And here this is like this, it's like this like this, and here is this, and here is this, and this. And far field is we having this electromagnetic waves propagates like this, radiate in this free space. So this is the near field, and this one is the far field, from considering the center of this to mid of this half of the field. So the antenna where we have put, this is divided into three regions, and the third part far field is our the working area. So the what happened when the reactive near field, we have taken the reactive near field, it is less than 0.62 and multiplied by root of the L cube by lambda, and the radiative field is less than and equal to 2L square upon lambda, and far field is given by the greater than and less than 2L square by lambda, and where lambda is the speed of the light and divided by the frequency. And one in this far field, two more constant. One is the for Fraunhofer frequencies, it is much greater than the physical length of the dimension of the antenna, and it is also much greater than the wavelength of the propagating EM waves in this free space area. So there are the distance for the far field distance. We are dealing this three main equations. For the near to free field, this is the reactive equations, and this is the radiative equations. For the near the this field between the half of the field of the radioactive waves. So this model assumes drawback is only to see the line of sight, direct line of sight, only the waves which transmit from here and it comes to receiver and it's directly fell on this. This is called the line of sight. On no others means or reflection or diffraction waves are considered in this model, yani ki free space model. So for this we having the equation power of transmitted receiver at distance d is given by PR, reference of the field, and multiplied by reference to the distance at which is capped of the whole square. This reference distance is always less than to the separation distance between transmitter and receiver, and it much greater than the Fraunhofer for reason, for frequency reason. So again we have rewrite this equation. Received power is given by dB 10 log PR do know, this is the reference distance, plus 20 log do not by D, that is the is greater than do not and df. This is the our two equations. So this model assume only line of sight. This come to the there is some more models to comes to remove this problem, and that model first to come is known as to remove the other to include the other signals that known as the two-ray model, which includes the feature of line of sight, which includes the features of line of sight signal as well as the reflected signal. Therefore, the free space model is only we have see the valid predictor for the received power for values of d, which are the in the far field of the transmitting antenna. The far field or the Fraunhofer region of the transmitting antenna is defined at the region beyond the far distance of the 4 point, and we have already seen in this figure. This is this region is fell in this region, so which is related to the largest linear dimension. If this is the largest linear dimension of the transmitted antenna aperture and the carrier wavelength, then Fraunhofer distance is given by d of is 2d square by lambda, where d is the largest physical linear dimension of the antenna. In addition, the far field of this DF must be greater than much greater than dimension of the distance between the transmitter and receiver, and it is also much greater than the wavelength. So therefore it is clear that equation which having for in Freeze equation is does not deal the path loss, that is tan log power of dt to t is equal to minus tan log gt gr lambda square upon 4 pi whole square d square. For this reason it is not valid, for does not hold if d is equal to 0. For this reason the large scale propagation model use a close in distance d naught. That why we have using this do not do, and as known this is the received power reference point. This is the received power reference point. Do notice the reference power point. So the received power, that is PR of d at any distance, that at we have assumed it at any distance, d is always greater than the reference point. The separation between transmitter receiver is much larger as compared to the received power reference point. In that condition, it may be related with the transmitted power, and the value of PR d naught, this reference point, may be predicted that the equation by this equation, and it is this equation, or may be measured in the radio environment by taking the average received power, and average received power many point which is located in a radiated distance forward from the transmitter. So if we consider that consider that our receiver is in between, that it may be include that the point which has been taken, there are another waves are propagating towards this received antenna. So that must be chosen such that it lights in the far field region, so that we have taken this d naught is greater than and equal to the d of Fraunhofer distance, and d naught is chosen to be smaller than any practical distance used in mobile communication system. Thus we using this equation, and the received power here, the received power in this is a free space at the distance greater than do not. So the whatever the power we have received in this is PLDV is greater than, and it is much greater than the reference power. So we write again, this is as VD is equal to PR D2, so it is multiplied by the difference of this whole square. So we getting this equation. In the mobile system, it is not uncommon to find it may change in many order of the magnitude over a typical several squares kilometers, क्योंकि it is the square of the distance, and because of the large dynamic range received by the receiver level, it is obtained in the 2 dVm and dVw. That is the reason which is covering in this units. It is expressed in the unit of dVm or dVw by simply taking the algorithm of the both side and multiplied by the 10. For example, if PR is dVm and received power, that PD dVm is equal to 10 log PR d naught upon 0.001 W and plus 20 log do naught upon D, and here the D is much greater than reference point and but less than the Fraunhofer distance, but much greater than the Fraunhofer distance, and PR do is in the units of watts. The reference D naught, the reference distance do not for practical system using low gain antenna in the 1 to 2 gigahertz region is typically chosen to be 1 meter in indoor environment and 100 meter to 1 kilometer in outdoor environment. So that the numerator in the equation, so that the numerator in equation PR d naught upon d square and PRD dVm 10 log PR D naught 0.001 W watts and 20 log D naught to D is a multiple of 10, and this makes the path loss computation easy in dB unit. So therefore we have chosen the two-ray model. So the two-ray model which here we cover is first we look at the figure. This one is the height of the transmitter and the distance where we kept our receiver, and height of this receiver HR, HT, separation distance D, and which kept on the surface of the earth, and it is assumed as a flat, and when the direct signal is fed on the receiver and when the signal is reflected by the ground and then comes to the receiver, so there is the two fields. One is the ELOS, another one first it's incident on the surface of the earth, then reflected back, which is given by ER, and the final received is EG. The angle between the incident rays and the earth is theta I, and angle between the reflected between the surface is theta 0. So the E total field is given by E line of sight plus E reflected field. So this is the two-ray ground